Hi students. In this video, we're going to talk about one of the first gas law type calculations, Boyle's law. We can do this now because we understand the concepts behind kinetic molecular theory, and we've defined pressure as being force per unit area. Another way, again, I'd like you to think about it is pressure is proportional to the number of collisions. As collisions increase, so does the pressure. So now we'll apply this concept of pressure and see how it relates to one of the other parameters in gases, the volume it occupies. So for all gas laws, and not just Boyle's law, there are four basic parameters we use to measure. One is P for pressure, T for temperature, V for volume, and as we've discussed in the past, moles. Here we're going to use lowercase n to represent the number of moles of our gases. If we know any of these three variables, we can find the fourth via calculation, and we'll discuss this later as we move forward in these videos with the ideal gas law. For now, you can understand that the ideal gas law is just PV equals nRT. P for pressure, V for volume, N for moles, T for temperature, and R will be a constant that we'll solve for. So first, let's take a look at Boyle's law. Boyle, at constant temperature and a constant amount of gas, changed the volume of the gas to observe pressure changes. And what he noticed was volume is inversely proportional to pressure. So what does that mean? If volume decreases, pressure increases. Again, not everybody likes thinking of terms in mathematical equations. So I'm going to rely on that simulation. And that simulation is so useful. Just as before, I'm going to go to the PhET and I'm going to choose the gases intro. And when I look at the gases intro, I want to show you a few things. Right now I have an empty container. It has a fixed volume at 10 nanometers. When I introduce particles, there's a certain pressure. Again, we've already discussed that pressure is related to or proportional to the collisions on the wall of the container. Now, I'm not going to introduce more gas here. Instead of introducing more gas, which would change the number of collisions, I'm going to just change the volume. So I'm going to have a constant temperature. I'm not going to introduce any more gases so that there won't be an increase to collisions due to the number of gas. What I am going to do is I'm going to change the volume. So right now my pressure is 11.7 atmospheres with a volume of 10 nanometers. If I half the volume, so let me bring that down to 5 nanometers, the pressure doubles. So what I see is, as I decreased the volume, the pressure increased. By how much? When I halved the volume, the pressure doubled. And I could even look at the number of collisions now, and we see that the number of collisions have gone up. Why? There's less space for these particles to move around, so they collide with the container's walls more frequently. Now, how can we use this with calculations? So again, this is just showing if I had 1 atmosphere and 1 liter, if I cut it in half, 0.5 liters, my atmospheres will double to 2 atmosphere. They are inversely proportional. As the volume decreased, the pressure increased. So that's essentially what Boyle's law is. The product, P times V, pressure times volume, is constant as long as the temperature and the moles don't change. So I could take initial conditions, P1, V1, pressure, initial pressure and volume, and determine what that value is. If I change one of the parameters, the other parameter is going to have to adapt. So if I change the volume, let's say I doubled the volume, now the number of collisions will decrease. So if I increase volume, the number of collisions will decrease because there's more room and there's less frequency of collisions. But I still have the same product. I could change these parameters again. I still end up with the same product. What does that mean? Essentially, pressure times volume always equals a constant. So pressure times volume always equals this constant as long as I keep temperature and the amount of gas the same. So I can set up this equation right here. P1 V1 equals P2 V2. And I can show what are referred to as initial conditions, a lot of times I, and final conditions, a lot of times F. So if I have a problem where I'm given a set of initial and final conditions, I can solve for the one missing parameter. If I read this problem, if a sample of helium gas has a volume of 121 or 120 mils, I know right away that's V1, and a pressure of 850 millimeters of mercury, that's P1. What is the new volume? I'm looking for the final volume, the change in volume, if the pressure has changed to 425 millimeters, okay? So if pressure decreased, what do you think happened to the volume? It must have increased. Well, how could we solve for it? Okay, we can use P1 V1 equals P2 V2, and we could directly plug in our initial volume, our initial pressure, and our final pressure to solve for V2, or we can solve for V2 algebraically and solve for it that way. Either way is fine. You can plug in the numbers directly or solve for it algebraically. Either way, you'll have the final answer of 240 mils. So we see that this makes sense. Pressure decreased, so volume must have increased to account for the fewer collisions. And we see that their final answer has 2 sig figs. So I hope this helps you understand the concept of Boyle's law in this video. And I thank you for your time. And I'll be making a new video for Charles' law. So thanks for tuning in.